Hello. Here we'll use orthogonal projection formula for making an arbitrary basis, turning it into an orthogonal one. That procedure is called orthogonalization. Or Gram-Schmidt process. The input will be, say, a subspace with an arbitrary basis. This process, this Gram-Schmidt process, will produce in a sequence of steps an orthogonal basis. So each step will be done locally, changing one vector at a time, and it will be making a new system orthogonal. The first step will be just renaming that the first vector in the original basis is now called the first vector in the new basis. So the first step is really trivial values. The second will make U2, will change it into something which will still generate the same subspace as the first two vectors, but now these first two vectors, new vectors, will be orthogonal. So what is E2? Well, to make it orthogonal is easy now, since we have orthogonal projections. Let's just take U2, the original vector we have, and take the difference of this vector with its orthogonal projection onto the previous vector, onto the subspace generated by the previous vector. And what it is literally, since we know what it should be, it will be just E1 with a coefficient, and the coefficient is the scalar product of U2 in E1 over E1 with itself. That is the first real step of Gram-Schmidt process, and the rest is the same. So the next step will be transforming U3 into something which will be orthogonal to the previous two vectors, which are already orthogonal. The same recipe to make it orthogonal. Let's just look at the difference between the vector and its shadow, its orthogonal projection onto the previously manufactured vectors. And again, the formula is known. It is E1 and it is E2 with some coefficients. And the coefficients are of the same structure. Denominators are scalar products of E vectors with themselves. Numerators are scalar products of the vector we are projecting with what we are projecting it onto. And continuing the same way, we will reach the final point where all the vectors are made orthogonal. The last step will be changing the last remaining vector UM by taking an orthogonal projection onto the previously manufactured vectors. And this time I will use the compact notation for the sum. Will be all the E's manufactured before. There will be m-1 of them. Coefficients will be all in terms of, this is m, in terms of scalar products. So that's what's called Gram-Schmidt process. That is an inductive procedure which gives us an orthogonal collection of vectors generating the same subspace. Even better, if we chop it, stop through this collection somewhere, then the set of previous first k vectors will be generating the same subspace as the first k vectors in the original basis. Well, let's put it into use. Let's look at an example. Let's look at a subspace in a four-dimensional vector space given by given as solutions of a system of linear equations consisting of just one equation. So solutions of just this equation where the sum of all coordinates is equal to 0. That is one equation which is already reduced to rational form. All but the first coordinates are free variables. We can make them whatever we like. So for example, we can make it 1 and then 0, 0. We can make 0, 1, 0. Why am I putting -1? I don't know. Or we can make 0, 0, 1. 3 choices, which will give us 3 linear independent basic solutions. And then what the first coordinate is determined by this equation that will have to be -1 in each of the 3 cases. So I guess I was eager to write this -1 somewhere. My hand was. And that is an arbitrary basis. As we will see, this basis is not orthogonal, but we will make it orthogonal and the first transformation is to do nothing to the first vector, just keep it as it is. So that is what E1 will be. We will have to compute E2 as whatever we have as a second vector minus its projection onto the first vector. So I'm using this formula. And the coefficient is a ratio of 2 scalar products. The denominator is the scalar product of this vector with itself, which is manifestly 2. The numerator, this number, the scalar product, is a scalar product of the vector I'm projecting, this U2, and the vector I'm projecting it onto, E1. And the scalar product is just 1, -1 squared. So I need to compute what this difference of vectors is. It's easy to scale everything by 2, or rather put 1/2 in front of the whole answer, and then take this twice, effectively, and subtract this vector. The result will be is, and the first coordinate -2 plus 1, you have -1, I have -1 again, and I have 2, and I have 0. Now is a little trick, not to deal with these pesky denominators in front of my vectors. I can still have orthogonality, perpendicular condition between the new vectors and the basis, if I scale any of the vectors by any random number. So for example, by 2. That is an adjustment to Gram-Schmidt process. That is not as Gram-Schmidt process tells us to do. According to Gram-Schmidt, we have to stop here, but let's be a bit more clever. Let's call it an intermediate answer, and the final answer for E2, or as I will write it here, will be just this vector without any prefactor. So yeah, E2 will be just this vector. A quick check that the vectors we have now are perpendicular. The scalar product has to be 0, and indeed, -1 with -1 is 1, 1 with -1 is -1, so the sum at this step is 0, the rest will be just 0. So yeah, they are perpendicular. Let's find the last. According to Gram-Schmidt, we have to take the last vector in our original basis and take out of it its projection onto the 2 vectors which we manufactured before. So I will write E1 and I will write E2. And then the coefficients in front of them are given by the scalar products. Denominators are always scalar squares, so that will be just 2, as we computed before. The sum of squares of this vector, which is the denominator here, will be 6. Numerators are scalar products of the vector we are projecting, with the vectors we are projecting onto. So this scalar product will still be 1, and so will be this scalar product. And that's what we need to compute now. And again, the prefactors I deal with by taking the common denominator out. And then this vector will have to be scaled by 6. And this vector will have to be scaled by 3 and subtracted. So negative 3 times negative 1, negative 3, 0, and 0. And this vector is just subtracted as it is. So the result is negative 6, positive 3, positive 1, negative 2, negative 3, positive 1, negative 2 again, negative 2 still, and then 6. And then maybe cancelling the common thing in between the greatest common divisor of all the coordinates and the denominator, which is 2. I will bring it down to negative 1, negative 1, negative 1, and then 3. And again, being more clever than the straightforward Gram-Schmidt process, I will forget about this prefactor by just scaling up by 3. And a quick check that this new vector is also orthogonal to the previously computed 2. So with this first, we only need to look at the first 2 coordinates, and again the scalar product will be positive 1, negative 1, totaling 0. With the second, we need to look at the first 3 coordinates, and we have positive 1, and then negative 2, and total again is 0. So these 3 vectors are now orthogonal. This is an orthogonal basis of the solution space. More to come later. See you then.